Welcome everyone to the European Society of Biomechanics Webinar Series. And today we will deliver a webinar in collaboration with the VPH Institute. Today's webinar is about ArtiSynth, which is an open source software for combined multi-body and finite element simulation. After the presentation, there will be a Q&A session, so please either during or after the talk, type in your questions in the chat or in the question box so that we can collect them and ask them to the presenters. So it's my pleasure to introduce to you Benedikt Sagl, John Lloyd, and Elaheh Elyasi. Benedikt is a senior scientist at the University Clinic of Dentistry at the Medical University of Vienna. His research focuses on computational investigations of the biomechanics of the masticatory system. He's responsible of the implementation of the inverse dynamics feature for computing muscle activations in ArtiSynth. John is a research engineer at the University of British Columbia, and he's the principal developer of ArtiSynth. And lastly, Elaheh is a biomechanical engineer at TwInsight and will show you an application of the software to knee modeling. So before starting, I would like to remind you all that all the webinars from the ESB are uploaded on the ESB YouTube channel, where you can find also other videos, such as recordings of the journal club sessions, awards presentations, and plenary lectures. So I would like to encourage you all to subscribe to get to know more the activities within the ESB. So I don't want to steal any more time from you. Thank you very much for being here, and we are very much looking forward to hearing your talk.
Okay, thank you very much for the introduction, and I will start off here with a little outline of what we're going to talk about. So I'm going to speak for about 15 minutes, giving an overview of ArtiSynth, and then Benedikt and I will do a live demo, and then we'll talk a little bit about how you install ArtiSynth and create models with it. And then Benedikt and Elaheh will describe some recent applications, and then we'll go to Q&A. Okay, so ArtiSynth is a simulation platform developed at the University of British Columbia. It's been an ongoing project for a number of years, and its principal purpose is to combine multi-body and FEM simulation in an interactive environment. So it is largely targeted applications in biomechanics and biomedicine, etc., but it is applicable to any system that is represented using Lagrangian mechanics. A little bit about motivation. So why did we actually do this? So it turns out that it's actually not that easy to find applications that combine multi-body and FEM in the same platform, particularly if you're looking at open source applications. And we did, in fact, want to have an open source system because we think these systems are very useful for fostering research collaboration. And open source is also very useful for allowing people to introduce new methods, algorithms, and techniques. So as you'll see, as we proceed, ArtiSynth has a very strong focus on interactivity. And another thing that we did was we were able to incorporate some techniques from CGI, computer-generated imagery, in order to speed up the simulation, particularly with regard to contact. So ArtiSynth fills a niche somewhat in between FEBio, which is an open source finite element software for biomechanics, and OpenSim, which is a relatively well-known multi-body simulator. So if you have a model you want to create that's essentially a multi-body model, but it has got some parts of it that involve deformable bodies or structures where you want to do stress-strain, examine stress-strain relationships, then ArtiSynth may be something you could consider. So I have a little video here. This video is actually on the website, so it shows some of the capabilities in toy form. This is the multi-body FEM coupling. illustrated in a basic way. We have elastic foundation contact. That's a relatively new feature. There's this interactive modeling environment that I mentioned. You can select components. You can modify their properties, run the simulation. We have support for soft constraints, compliant constraints, which is useful for a number of things. There is a scripting interface via MATLAB if you want to do that. We have 6-degree freedom frame-based springs. So this is like bushings in OpenSim. There are ways to connect point-to-point muscles into FEM models by attaching them to various nodes. We have a variety of materials. We have rotated linear materials, shell elements in either membrane form or full shell element form. We embed muscle activation into finite element models. We have mesh embedding, skinning. We also have wrapping, and in particular, we have wrapping for general 3D surfaces, muscle wrapping, so that's relatively useful. And finally, there's the ability to do rigid or non-rigid registration built into ArtiSynth as well. So I will quickly talk about some of the components that ArtiSynth provides. So we have particles, we have point-to-point muscles and springs, there are rigid bodies, there are joints. ArtiSynth does not use joint coordinates to represent configuration. Instead, rigid bodies are represented using full 6-degree freedom coordinate frames for each body. And this becomes relatively, well, this is necessary if you want to connect a couple of rigid bodies instead of by a joint, if you want to connect them by some flexible structure, such as an FEM model or frame spring, then you're going to need that full 6-degree freedom representation. For finite element models, the nodes of each FEM are represented essentially as particles, and then the elements themselves become the equivalent of 3-dimensional springs. We have markers. These are points that can be attached to either a rigid body or to the elements of an FEM, and that's useful for connecting point-to-point muscles and other things. FEMs themselves can also be attached directly to rigid bodies. So typically what we do is we'll take the nodes of an FEM and attach it to adjacent bodies. So in this demo I'm showing here, the nodes that are illustrated in red at each end of the FEM are connected to the blocks at either end. So for the FEMs themselves, we have a variety of standard geometries that you can create. So cylinders, toruses, partial discs, beams, ellipsoids, etc. But most commonly, you're going to want to use unstructured geometry, particularly in a biomechanical domain. So there are 2 ways to do that. If you have a triangular mesh, then we have TETCHEN embedded into ArtiSynth, and that can be used to create a volumetric tetrahedral representation from the triangular mesh. Or if you have geometry represented in the file format of some other application, then you can import that directly into ArtiSynth. So we have importers for that work in a variety of file formats, including Abacus and ANSYS, etc. Also have embedded geometry. So given an FEM model, you can embed surfaces and polylines directly into the model, and then they will deform as the model deforms. And this is actually useful for a variety of things, including speeding up the simulation and making the simulation more robust in some circumstances. And I think Elaheh will allude to that in her talk. So I mentioned that we have muscle embedding into finite elements. So this is done in 2 possible ways. One way over here showing on the left is you take FEM elements and you just connect them using point-to-point springs directly. The more correct way from a constitutive model point of view is we have auxiliary materials that are anisotropic and actuated along a direction that is associated with a particular muscle activation. And those auxiliary materials, their effect is superimposed on top of the base material of the FEM. There's a number of other components that these were alluded to in the demo. So we have multi-point springs and wrappable structures. We have 6-degree freedom springs. Collision behaviors are represented as components. There's a variety of graphical components, including a DICOM viewer. And I also mentioned that we have skinning, so you can wrap a skin mesh around some combination of rigid bodies or finite elements. All of these components are combined within your model into a component hierarchy. There is a standard form for the hierarchy, or you can create your own arrangements of components. It's up to you. There's a navigation panel that allows you to examine and select components, and also components can be examined and selected inside the viewer. So model creation, we use Java, the programming language Java, essentially as a scripting vehicle in which you import geometry for your model, create the components, set their properties, and then assemble them into some final model. So we'll talk a little bit more about that later. Components, as I mentioned, have properties. So if you have, say, an axial spring, it might have properties like length and material. If you have a rigid body, it'll have properties like position, orientation, inertia. Properties can also be connected to probes, which are channels of input and output data, which are used to either control the simulation or monitor its output. So in this video, I've got an input probe along the top here that's controlling an excitation for these muscles. And at the bottom, I've got an output probe that's recording the X, Y, Z positions of this green marker point here. And these probes are all arranged inside a timeline that you can use to view the data. Now, in addition to probes, you can also create code-based controllers and monitors, so you can write your own code that's called before or after each simulation step to control the simulation. And so let's look at time stepping. So what actually happens is ArtiSynth runs generally a fixed time step, which you can set to whatever is required. Typical time steps are perhaps 10 milliseconds down to maybe 1/10 of a millisecond or lower, depending on what's happening. At each time step, we increase the time of the simulation by the step size h. Then we read our input probes, apply any controllers. Then we integrate the model from T0 to T1, so from the beginning to end of the time step. Apply monitors, write output probes, update the time. There are scripting interfaces, so we have Jython and also a scripting interface in MATLAB. And this is very useful if you want to run a number of simulations with different inputs, outputs, and properties, and do this all in some sort of batch form. Okay, and now we'll show just some quick video clips from some older applications. This is a finite element model of the masseter. It's the main muscle used in chewing. It has a complicated structure, tendon sheets, embedded fiber fields, etc. And this model was used to study the effect of that structure on chewing force, and that was done in connection with a multi-body model of the jaw. This is an FEM model combined of the face and other parts of the oral cavity, including an FEM model of the tongue, dynamic model of the jaw. And the purpose of this was, well, there are several purposes, but one was to actually study tongue motions associated with different speech sounds. Lastly here, this is an FEM model of the foot by our collaborators in Grenoble. So they took a line-based musculoskeletal model of the foot and then embedded that inside a 3D model simulating the foot soft tissues. And this was done to study the pressure, the contact pressure patterns when the foot makes contact with the ground, in order to help patients with diabetic neuropathy. Okay, so that's a quick overview, and now we're going to do a live demo. And what we're going to do is Benedikt is going to drive the demo, and I'm going to narrate it. So this has worked in the past, so hopefully this will go well now. So we need to move the screen over to Benedikt.
Okay. You should see a jaw model loaded in ArtiSynth.
Yes. Okay. Perfect. Okay, so this is, so we have Benedikt has ArtiSynth running here. This is a model of the human jaw. It was created by Ian Stavnus here at UBC in order to study chewing and mastication. And you can move this model around in 3D with a mouse. You can pan, zoom, shift. If you have a 3-button mouse, then this is all done with the middle mouse button. If you don't have a 3-button mouse, the system will detect and give you a different set of bindings. You could go over to your settings and open up mouse settings. That will tell you what bindings you have, and you can look there to see what does what. You can also you can change the mouse bindings, or you can consult the user interface guide for more information on this. Okay, so at the upper right corner, we have a set of play controls. If you hit the start button, that actually starts the simulation. The simulation is now running. The simulation runs in real time. You see the time counter clicking up there. If you hit the pause button, that stops the simulation. If you hit reset, that resets the time back to 0. Okay, when we run the simulation, we can do some other things. We can actually activate muscles. So there's some control panels over on the side. So 7 muscles that can be interactively controlled. So these control panels are created by the model application. And so yeah, you can create control panels as well. I didn't mention that in the overview. There's also a pull controller, which is a set of tools over on the left. The bottom tool is the pull controller. And if you click on some part of the model and pull, then it just applies a force. And so this is useful for just kicking a model and seeing how it responds to particular types of force inputs. Now there's a navigation panel. Navigation panel. So we open up the nav panel and see the structure of the jaw model. We have rigid bodies, we have frame markers, body connectors, etc. We can open up rigid bodies. You can see different rigid bodies. We can select them. You can select components in the navigation panel, or you can also select them in the viewer. So say we select one of those axial springs. Open the properties, and we'll see all the properties for that axial spring, including material. So if you just click the pull down menu on material there, you see some of the different spring type and muscle type properties that we have. So this can be obviously set in code, but it can also be adjusted in real time. We can also control rendering properties. So for instance, if you select the jaw, we can open the rendering properties. There's a number of things related to just how this thing looks graphically. So we can set the face color for the jaw, say. So instead of this bone color thing, we set something else like that. And finally, we can control visibility. So if you go over to rigid bodies in the navigation panel and click on, I guess, cranium, you notice that the cranium's not actually visible, but we can make it visible. So it's actually there in the model. You didn't see it, but you can control visibility directly there. Okay, so that's the jaw model. We have another model. This is now we have an FEM. This is a toy model of 2 blocks and an FEM and a joint up in the upper left corner. Okay. So we can do a few things with this. We can so we reset. So let's select the left block, open its properties. We can make that left block non-dynamic. So now it's so now when we play, it basically. So use the pull controller if you wanted to pull around. Now we can let's reset, and let's change some properties for the FEM model. Actually, select the FEM model, its property panel, and you have a number of materials there. Materials. So, for instance, right now we have a linear material. We can open up that linear material and change its elasticity, so we can make it a little less stiff. Just to show you what that'll do. Okay, so then we can also we can control the visibility for an FEM. So we can turn off the mesh rendering, for example. So over there, the surface mesh for the FEM is currently being rendered. We can turn that off. Now we're just rendering the elements and the nodes. We can turn off rendering of the nodes as well if we want. Go to the navigation panel, select the nodes, so make the nodes invisible. You can also render elements individually. There's something called the element widget size. So if we set that in the FEM model, increase that, now we get little small renderings of each particular element. And this is useful for selecting individual elements if we want to do that. There are some editing capabilities that I'll just show off briefly. So if we select the, let's select that right block. We can delete it. And we can also add marker points to, so there's a tool for adding markers. So we can add markers, say, to the, I think you'll need to add that to the left block. That. Okay. So so we made some edits to this model. Let's save and load it. So we'll go over to the file menu, open up the file menu, just do save as, enter some file name, save it. Now let's load it back in again. So there's an ArtiSynth file, ArtiSynth store. The ArtiSynth file format is something like JSON. It's not an XML format, but it's another type of text format. So that's useful. So you basically edit your models and so, pass them around or store them in file format. Even though models are often created in code, we do have a file format. So okay, one more model. FEM model of the tongue. This is created by, again, people in Grenoble, and this has been used a number of times. You'll notice when Benedikt plays the tongue, it is flexing. And down at the bottom, you see a timeline, and there are a number of probes. These are input probes that are used to control the excitations for a number of the muscle elements in that tongue. And some of them are muted, but some of them are active. We can mute the entire thing, so we can turn off the timeline. So now when we play, nothing actually happens directly. The tongue just settles under gravity. Let's have a look at those muscle groups. So we go to the navigation panel, and the nav panel, navigate down to the tongue model.
Great. My nav panel didn't open.
Okay, right, muscle bundles. there. So these are the muscle bundles. I mean, the other components for the FEM model, right? There's a list of nodes, there's a list of elements. These are the muscle bundles. Let's to have a look at the muscle bundles. Let's make the surface mesh invisible. Actually, you can do that right over on in the control panel, just at the very bottom of the tongue control panel there, where it says shaded.
Where?
Right there. No, over in the right, down at the bottom. Surface rendering. The custom control panel for the demo. There.
Oh, sorry.
Yeah. Okay. Okay. So now we're not seeing the surface mesh anymore, but we're seeing the individual muscle bundles whose fiber directions are rendered in different colors. We can mute the timeline. Let's look at just to get a better sense of what I'm talking about. Zoom in a little bit on the tongue, and select one of the fiber direction, one of the muscle bundles in the nav panel. If you could do that, just any one. Open up its properties, change and set its direction fiber length, and you should do that. And you should see that getting longer.
Yeah, it's the orange one back down here.
That's right. So that's just one of the muscles. Oh, and then when we play this thing, the timeline is muted, but we also have another control panel here that will let you set the excitations for that. So again, practically like that. Okay. That's the end of the demo show.
I think that means back to you, John, right?
Back to me. Okay, so now we're going to. All right, installation and model creation. So if you want to use ArtiSynth, so the first place you should go is to the doc folder on the website, and there you will see links to a number of different documents. The three most important ones are the user interface guide, which talks about the interactivity. That's the stuff that Benedikt and I were just showing off. There's a modeling guide that tells you how to actually create models. We'll get back to that in a minute. And then for purposes right here, there are installation instructions. If you go to that page, you'll see a number of links to a number of different install guides for different types of configurations. And the one we're going to do here is the GitHub Eclipse install for Windows. So what we're going to do is we're going to install ArtiSynth directly from GitHub into the Eclipse IDE. So there are three parts to this. So first of all, you need to have Java installed on your machine. If you don't, you should install a Java JDK from oracle.com. I should say you should actually have a Java JDK, so that's a Java development kit. So it comes with a compiler as well as a runtime executable. So install that. We recommend actually the older Java 8, but it will work with newer versions of Java. And then you can install the Eclipse IDE. IDE stands for Integrated Development Environment. This is an application that lets you create Java programs, compile them, and run them. And you install that from eclipse.org, and that's relatively easy to do. And let's assume then if you have done that, then you can install ArtiSynth Core from GitHub, and that is relatively easy to do, as I'm going to show now in this screen capture. So this is the Eclipse IDE running, and now we're going to import an existing project from Git. Click Next. We clone the URI, and the URI for ArtiSynth Core is already loaded in there. We only need the master branch, and pretty much we just keep hitting Next here. It's checking out the ArtiSynth source here. We're going to hit Next again. And now ArtiSynth is loaded into Eclipse and is trying to compile. but it can't because there's one more step required because we need to download some native libraries. So you go to the ArtiSynth install directory that you've just downloaded, go to the bin folder, and then you click on ArtiSynth update libs, and it will pull in all the ArtiSynth libraries, and then you refresh your project, and now it will compile. This will take a couple of seconds here while it is compiling, and that will be done. Okay, so then you go type run, and we have a predefined run configuration in that install, and up comes ArtiSynth. We go to demos, and there's our Hex 3D block. Yeah. So not too daunting, hopefully. All right, once you have ArtiSynth installed, then you go to the modeling guide, or you can go to the modeling guide, and there are a lengthy set of directions for how to bolt together models of different types, multi-body models, FEM, combinations, joints, constraints, collisions, all that. It's all described in the modeling guide. And now we're going to pass the screen back to Benedikt, who's we're going to have a look at the source code for that thin 3D block example. And I'm just going to talk through it, and Benedikt's going to make a couple of modifications just to give you a sense of what we're actually dealing with here.
So you should see some source code now, right?
See source code, yeah. So let's just go to the top here quickly.
So just to show that again, this model we're looking at, yeah.
Exactly. So at the very top, there's a bunch of there's a package declaration. There's a bunch of imports where you import different packages. Hide that, and then the model itself is here, and there is basically models you create a build method, and the build method creates a mechanical model under which we're going to assemble all the components. And then if we look here, we see some blocks of code. So the first thing we do is we create this hexahedral mesh, FEM mesh there, and set some material properties for it. So that's from lines like 31 down to 38, and we add that to the mechanical model. And then we create a couple of blocks, the blocks on each end, and rigid bodies. They're created as boxes with a given density. We set positions for them, and then we call this attach FEM to rigid body method. And let's just show that. That's down at the bottom. Just scroll down to the bottom, I guess, of the thing. Yeah, it's a little convenience routine that I wrote there. And what this does is it goes through all the nodes in the FEM, finds the ones that are very close to a specified rigid body, and if it's within a certain distance tolerance, it calls the mech model attachment constraint to attach it to that rigid body. Okay. Now we just scroll back up a little bit. And yeah, so we created those two blocks, attached them to the FEM. We're almost done, except we also create that hinge joint there and position it in world coordinates, and then connect it, use that to connect the left block to ground. The last bit of code starting at line 65 are just setting render properties. What color do I want things? What size do I want the spheres on the FEM nodes? Do I want them to be spheres? That sort of thing. Okay, so we can just make a change here. So let's just change something in the code. So FEM surface rendering is currently set to shaded. Let's set that to stress. Yeah, stress. And do you want to change something else? Do you want to make a block bigger, Benedikt?
Sure. Let me see. Where's the block? Here's a block.
Box. Okay, so it just changes the dimensions of the box there. Okay, and compile, and there we are. It's a slightly different model, and this is just showing off also some of the ability to render stress and strains on FEM surfaces. Okay, that's our very quick coding demo to give you an idea of what model creation is like. And now we're going to pass the screen to Elaheh. Thanks, Benedikt.
Okay, yeah. So you're seeing my slides?
Yes.
Perfect. Yeah, so I will be very quickly showcasing some of the modeling activities that we've done with ArtiSynth for the lower limb. First step would be just to show you the modular lower limb model and then how it was used for 3 different applications. Our modular lower limb model was constructed using imaging data from a subject, and given that ArtiSynth provided the possibility of building combined multibody FE models, we benefited basically from this flexibility and created multiple representations of the same structures in our model. This way, it was possible to modulate the model and construct models with various levels of precision for various applications that we had envisioned. So one of the advantages of having such a modular model for us was the ability to quantify our modeling choices and their impact on the metrics that we were measuring. For instance, we did that in a simulation of passive deep knee flexion, and we quantified the difference in the patellofemoral kinematics predicted by a model with fully finite element representations of the quadriceps muscle group, which you see on the left video, versus a model with multi-point muscles that you see on the right. The results were compared obviously against validation data that we have available from MRI images at various flexion angles to see like the amount of precision that we were sacrificing by using multi-point muscles. Another thing that we tested was also to use muscle surfaces embedded in a coarse FE mesh for the 3 vastus muscles. And in that way, we could still include the effect of contact forces between the volumetric muscles that are kind of like compacted together in the thigh. But we could reduce the computational time of the model to 1/3 of the fully FE model that you saw in the previous slide. With relatively small sacrifice on the patellar kinematics and stress distribution that we were computing for the rectus femoris muscle. Another simulation that we did was related to high tibial osteotomy, which is the surgical intervention to correct the alignment of the lower limb to opening a wedge on the tibia. And what we wanted to study here was to see if the distalization of the patellar tendon insertion due to wedge opening has a significant effect on the position of the patella postoperatively. So for this, we use the FE quadriceps muscles, we use the FE patellofemoral cartilages because we are like interested in a very precise kinematics of the patella and also interested in the stress fields in some structures. One final simulation that I will be showing is the gait simulation. We had gait analysis data from the subject and we use it for an inverse dynamic-based optimization to compute the muscle forces during a cycle of gait, which was done using a toolbox in MATLAB developed by one of our collaborators called Raphael Domain. And the computed muscle forces then were injected into a forward dynamic model in ArtiSynth that had a deformable knee, including FE cartilages and contact and so on. And the idea was to evaluate the inverse model and test various optimization functions through this like forward kinematics simulation in ArtiSynth. It's just worth mentioning that although ArtiSynth is not designed for running gait simulations particularly, but the fact that there was like many possibilities such as controllers, monitors, joint definitions, muscle material models, and so on facilitated the process of building gait simulation and extracting the metrics that we wanted for the model. So that's all that I wanted to show. With that, I thank you, and I pass the mic back to normally Benedikt, right?
Yes. Thank you very much, Elaheh. I hope you see my slides now. Perfect.
Yes.
So thank you very much. I brought 2 more examples of kind of modeling projects with the aim of showing off some more of the capabilities of ArtiSynth. So the first thing we want to show is some of the spine modeling work that my student Thomas Holzinger did here in Vienna, and which also uses the OpenSim import and ArtiSynth. So he was interested. So spinal cord injuries have a severe impact on people's life, as you know, and they are quite commonly occurring in sport injuries, and cervical region injuries are especially predominant in rugby. And since the investigation of modeling of the injury process is hard to investigate in vivo, computational models are very useful for these kind of investigations. And our collaborator Dario Cazzola at the University of Bath spent the last few years working on rugby and other spine biomechanics modeling studies, and they developed this very nice OpenSim model of a rugby player, and they use these bushing elements, which are 6 degrees of freedom springs, where you can define different stiffness for each of the translation and rotational degrees of freedoms, to kind of mimic or include all of the soft tissue in the joint in these bushing elements. And we wanted to do some spine modeling work, and based on Dario's work, and didn't want to start with building a completely new model, but wanted to start with the model he already developed. And for that, there's something called the OpenSim importer or OpenSim model importer in ArtiSynth. So first of all, I want to stress that this is still work in progress. Not all components, not all OpenSim components are currently supported in ArtiSynth, and I'm sure there's a bug here or there somewhere hiding, but we'll eventually get all of them fixed. And as the title kind of suggests, what this tool kind of allows you to do is import OpenSim models, so .osim files into ArtiSynth, and base your model on a pre-existing model, so that you don't have to redevelop something somebody else already did. And while it's still work in progress, it already supports what I would consider the most of the major components. So obviously rigid bodies are supported, multi-body joints, most of them are supported, including OpenSim custom joints. The most commonly used muscle models are supported, and also things like wrapping bodies, external forces, springs, and so on. So in a best case scenario, you can have everything cleaned up, and to import an OpenSim model into ArtiSynth, you basically just have to define an OpenSim parser, give it the OpenSim file you want to load, define the geometry path where to find all the mesh surface, the surface meshes, then create the model, and then you get an ArtiSynth model that represents, so it basically replaces the OpenSim components with the closest components we have in ArtiSynth. So for example, for these bushing elements, we have something called frame springs, which is our implementation of a 6 degree of freedom spring. So that was the bushings were replaced by frame springs. And what Thomas then did, he was interested in more detailed investigation of the biomechanics of the intervertebral discs. So he removed the frame springs and then replaced them with finite element IVDs. And now we can do things like investigating head first impact with more detail for the actual biomechanics of the IVDs. The second example I brought is some of our shoulder modeling work, and especially the tracking control in ArtiSynth. So with tracking simulation, tracking controller, very briefly, the most straightforward way of running such a biomechanical muscle-driven simulation is measuring EMG and measuring muscle activation, inputting muscle activation, and then computing forces and movement dynamics and so on. But sometimes measuring EMG is really hard if there's a very important small muscle next to a very large one, or if muscles are overlapping each other, for example, in the face. And so sometimes it's maybe the better way to measure the motion of a body and then use some kind of optimization to try to find the best fitting muscle activation pattern. So for this dummy example, this green point is basically showing you the target motion of the white point in the middle of the circle. And now if you enable the tracking controller, the simulation finds a muscle activation pattern that best helps you track this motion. And obviously, this is something that other simulation toolkits can do as well. And most of this work is focused on motion tracking, but there are other things that might be important for muscle activation, for example, forces. So joint reaction forces, or in my case, it's often about chewing or tooth grinding. So you you might have forces that are not necessarily directly related to motion, but still should be implemented in your optimization. And often these forces are added as external forces to the simulation, which can make the simulations rather unstable, especially if you can't measure the forces, so you don't really know where to start with your external forces. And also, obviously, it's more stable to include the forces in the optimization instead of adding them at the top of the optimization. And then another thing that is especially interesting for shoulder modeling, which I will show in a second, is reaction force constraints. So we published this method based, again, using the OpenSim importer on an OpenSim shoulder model by Sagl et al. And I brought two examples. The first one is pulling on a handle, and the second one is the use of the constraint, the reaction force constraint. So here the left column basically simulates pulling on a handle using an external force, and the right column shows pulling on a handle using a bilateral constraint and a reaction force target as handle. So you see the first two pictures in the top simulate pulling with 100 Newton, and you don't really see any difference between the two methods. But when you increase the external force of the target to 300 Newton, which is way more force than the model is able to actually create, the version with the external force goes unstable. So if this would be a video, the arm would just fly around like crazy, while the method with the tracking controller simply just creates as much force as possible and then stops and keeps the model stable. And interestingly enough, so that's what the simulation looked like, the 175.5 Newton maximum pulling force fits quite well in actual literature data on maximum pulling force. And so the second example here is the joint reaction force target. The shoulder is often modeled as a kind of ball and socket joint in multi-body models. And this means the shoulder can't dislocate at all. But in real life, muscle activation is actually needed to increase shoulder stability. So this leads to rather unrealistic muscle activation patterns being computed in tracking simulations. And there's actually literature on how the relationship between compressive and shear reaction forces has to be, so it basically has to be inside this cone for the shoulder not to be dislocated in real life. So what we can add here is a reaction force constraint that makes sure that the reaction force stays inside the cone of physiological reaction forces. So here are two examples of shoulder elevation simulations with and without the stability constraint. And you can see, obviously, there's a clear difference in shoulder reaction force. And then here's the mean muscle activation for both approaches. And you can see that obviously that the difference in reaction force has to come from somewhere, and we compute quite a different, hopefully more realistic muscle activation pattern using our method. And lastly, since I'm working at a dental clinic, I just want to briefly show that all of this is not specifically created for spine modeling or shoulder modeling, but actually we here, for example, have a jaw model with finite element temporomandibular joint discs that uses here a tracking simulation of motion to create chewing patterns. And then we change the foot stiffness and stuff like that, and saw all that change biomechanics of the joint. And here we have an example of a tooth grinding simulation where we have a motion target and a force target and combine basically everything I've shown you before into one simulation approach. Okay, these were my very fast two examples. At the end, I think we should acknowledge some people. I don't know, John, do you want to take over again?
You know all those people.
Yeah, I know. So first of all, Sid in the files is the PI of the ArtiSynth project, and Ian Steffen is a professor at the University of Saskatchewan who did a lot of work on ArtiSynth itself and also helped with slides and videos. And the same is true for Antonio Sanchez at the University of British Columbia, who developed a lot of methods in ArtiSynth and also was part of the combined effort to get these slides done. And then some funding sources. And lastly, thank you all for listening, and we're happy to take any questions.
Thanks, Benedikt.
Well, thank you very much. It was a very interesting presentation. We get really a lot of knowledge into ArtiSynth, and I think that now there are a lot of people ready to download the software and start to get some hands-on. I saw that we have some questions from the audience, so I think we can start from that. So the first question is there a novel validation approach since you combine two big technologies that have very different approaches in validation terms? For example, anybody often uses muscle activity tracking for validation, and finite element model is mostly validated using mechanical tests. Is there a combined approach for your system?
Who wants to take that? No, I can start.
Okay.
So I think for the most straightforward way probably is to validate each of the parts individually, right? So you can still validate muscle activations or motion using motion tracking and EMG, and things like the material property, the material models and so on can still be tested using cadaveric tests or simple static simulations. It obviously will be tough to validate things like TMJ or FE stress during dynamic motions, because you probably won't be able to measure it in vivo, and you can't measure it ex vivo because you won't get muscle activations. What we tried, or what we did once, was that we basically used MRI data at end positions of functional movements to kind of get the jaw position and the position of the cartilage disc and its deformation, and checked how, if we simulate the same motion, how these positions and deformations fit together. That's obviously a workaround, but I think it still gives you some insight on how well the model performs.
ArtiSynth is a toolkit, right? So it's something you use to create the models. The validations required for models really depend on the model and the particular application. So in some sense, is a little bit beyond the actual task of validating, is a little bit beyond the scope of ArtiSynth itself. But particular modeling arenas are going to have different requirements. Elaheh, do you want to say anything to that, or?
Yeah, I totally agree with that. Like as Benedikt said, based on the application, it's possible to add multiple layers of validation. Basically, like the same thing exists for the knee biomechanics. For instance, the data that is available through the Grand Challenge or the CAMS knee project, or those are example of the data that is available, both at the level of like the muscle forces that are predicted, and at the same time kinematics, at the same time the joint forces, the like contact forces, and so on. So based on the application, for sure, it is possible to do multiple layers of validation for the context to be used.
Okay, thank you for your answer. Another question may be the application of ArtiSynth for prosthesis, to the prosthesis area. So if you have ever tried to investigate some, let's say, post-operative scenario with some prosthesis and to model the kinematics.
Right, I didn't quite understand the thrust of the question. So what did you say it was?
So if you introduce, let's say, prosthesis into the model, and you try to see how the kinematics, how the muscles are activated when there is also an external body as a prosthesis into the system, mechanical system.
Yes, I mean you could certainly do that. A lot of the work we've actually done is slightly different. It's not so much introducing a prosthesis, but it's modifying the model in some way that emulates the result of a surgical intervention. So we've done a fair amount of work with that. So the jaw model that Ian worked on a few years ago. So one of the interventions we were considering was hemimandibulectomy. So you cut away a portion of the jaw, and then this has some effect on the resulting musculature, and then you try to reproduce a motion, some sort of target motion or some target task. In the case of the jaw, generally related to chewing, and see how well see how much function has been impaired, right? So yeah, I mean, the same thing would apply to introducing a prosthesis, and you can modify the model in any way you want. And I assume you're referring here to the inverse simulation. The inverse simulation giving you have some target you want to track, and then you figure out what the muscle activations are.
Okay, thank you. Do you have other questions, Chiara?
Yes, I don't see other questions in the chat, but I'm talking to the audience, so if you want, we still have some minutes, so you can type in your questions. I actually have a question that I think could be of interest for the people here listening, because since there is also some coding part, I guess there is a learning time to get to know how to use the software. So I'm wondering, yes. Yeah, do you have, yes, or do you plan any classes or courses where people can attend and learn how to use it? Or it's more like direct contact with the people that wants to know how to use the software?
Right. So most, not all, but a lot of the users that we know about, we have had contact with. You could certainly email us. There's an email address on the website, and you can get contact with us that way, and we're happy to answer questions and such. Now, I have people have sometimes asked me, well, if I want to learn a little bit of coding in Java, what do I do? I actually have a cheat sheet that I've kind of prepared. What it actually does is refer you to the Oracle Java tutorial, which is a fairly nice introduction to Java, and it just gives you the parts of that you should pay attention to. There's a lot that you don't need to know. And in fact, one of the issues that comes up is, I mean, this is a general problem with modeling and complexity, right? So you have this complex system, and then we respond to these complex systems by adding some other system to make it complicated, but that adds more complexity. The Eclipse integrated development environment, which we showed here as an example of something you use to compile and run your programs, that thing is possibly more complicated than Java if you really get into what all it does. So trying to manage that complexity is something. Yeah. So I mean, we're certainly open to having tutorials. We have done workshops at conferences in the past, and we're probably overdue to do one of those. So something a little bit longer than this forum. We get into a little bit of coding exercise and something. The idea of actually putting a series of videos out to YouTube, so having an ArtiSynth YouTube channel is maybe something we should think about as well, just to get people over a certain hump. But once you've been able to do model development in code, you generally don't want to go back, because it gives you an awful lot of ability to do things and control things and set things up just the way you want. So,
and I think it was a little bit, I don't know how so we tried showing a little bit of coding, but due to the limited amount of time, it was probably very fast. But it's really, Java coding sounds a lot more complex than most of it is. It's mostly scripting, right? It's predefined functions that are kind of take together, as long as you don't start to develop new methods or new approaches, right? Then obviously it gets more into coding. But to create a model from existing ArtiSynth components is more, if you have some basic idea of coding, I think the coding part should not be the problem. And also want to emphasize again the modeling guide that mostly John created, which is a great resource. There's always, like, there's not only descriptions of the different components in ArtiSynth, but there's also a lot of simple coding examples and demos that are all part of ArtiSynth core. So you can all run the code, change stuff, and you have the code snippets at the relevant positions in the modeling guide. So I think that also helps a lot to get started in ArtiSynth.
That's great to know. That was
That's
actually
right, yeah.
my second question.
Yeah, right. So there are, right. So the modeling guide, it's about 300 pages long. It could be longer. There are things in ArtiSynth that are not in the guide yet. But most ArtiSynth components, there will be a tutorial example of using that, a toy example, and that will be maybe a page or two of code maximum. So you can sort of get in there and take it sort of by piece as you want. So,
Perfect.
and all of that is included in the ArtiSynth distribution.
Good. Actually,
Great,
more
thank you.
questions are coming, so I think I will go quickly if you have still time to answer these.
We'll do a rapid round.
So the first one is about material properties. So are there also more complicated model as compared to linear elastic or hyperelastic? Of course, only for the finite element components.
Yeah, so most of them are linear and hyperelastic. We have a background project to introduce poroelasticity. There is also the ability to, we have a rest, what is it called? To change the, I'm forgetting the terminology here, but effectively an initial stress component that can be changed, and this will give you plastic deformations. But the poroelastic thing is, that's in the works, and that's needed for higher accuracy cartilage simulation. So I think Benedikt is possibly one of the users of that. Right.
I'm looking forward to that, but there's a lot of things that need to be done and not too much time, right?
Yes.
Thank you.
I think there's also viscoelasticity,
I should
right?
also point out that you know, a material property is, there's a couple of functions you provide: compute the stress and compute the tangent matrix. And you can write your own component that does that, and then just you have your own material. So if you have something interesting that you want and you know how to do it, then it's relatively straightforward to incorporate that into ArtiSynth yourself.
That's great. Thank you.
Okay, thank you very much. And last question for today is, which are the future developments and potential direction for ArtiSynth? So basically, which are the next steps that you're planning for developing the tool?
Yeah, so that is a good question. Yeah, so what's the roadmap, right? So I would say there's a couple of things. So first of all, that OpenSim importer, we'd like to get that polished off more. It is in the package, although it's not actually, we haven't documented it yet because it's somewhat in development. So that would be good, right? Because then you can take OpenSim existing models and then add other things to them. So there's that. The registration aspect of the system. So I mentioned at the end of the video, so non-rigid registration capabilities. So to flesh that out a little bit more and make it easier to do subject-specific modeling. So that's something that that we're looking at. Increasing like support for actually poroelastic models. That is in the works. So those are things. Benedikt, is there?
Yeah, so the poroelastic material is kind of high on my to-do list. Also always interested to kind of improve or create new terms and get the inverse controller to work with more different targets and things like that. That might be something we might do in the future. And also, I mean, if some of the listeners are interested and think that there's like a key feature that could make this a way better software, I think we're also always happy to talk and listen, and maybe it's something that's not crazily complex and might make it on the to-do list, right, John?
Yes. Well, I mean, one thing that we do want to do, and this was, we would like to flesh this out a little bit more. So maybe just mention in closing, and this was part of the initial vision of ArtiSynth, is to create a bit more of an open source community. So we want to encourage people who create models with ArtiSynth to make those models available on, say, GitHub or in some repository form, so other people can download them, and then they would be automatically linked with the appropriate version of ArtiSynth with which they were created, so other people can use these models and we get better sharing of resources. That's important, and we'd like to get a little bit more of a active development community. We have had a bit of that in the past, but people come and go. A lot of the developers tend to be graduate students, so they're, it's on while they're students, but then they go and they work for some other place and they're no longer active. But yeah, to try to create more of that. So that's what we'd like to put some effort into that as well.
Thank you very much. I think that would be great also, because this is a bit the objective of open science, open research. So
yeah, and yeah, I mean, I think there's still, I get mixed responses to this. I mean, some people, their data, you shouldn't do that. Yeah, not if you're, in an academic setting. I think you need to release the data, release the code, make it useful, have people work with it, and it's just part of the process. And I think things can move in more interesting directions at a greater speed if we do that.
Yeah. So I think we are at the end of the webinar. We are a bit out of time, but I think it was very good because people were really interested. So there were a lot of questions. And yeah, I would like to thank you very much again. I think it was very clear it's very clear what are the capabilities of these toolkits. So yeah, and also to the audience, if you have any questions or suggestions or ideas, just contact them. This video will be uploaded on the ESB YouTube channel, so you can go through it again and again, and we will put them there also, the contact of John, Benedikt, and Elaheh. So thank you very much again for being here, and yeah, wish you all a nice evening.
Very much.
Thank you very much.
Thank you.
Bye.
Bye.
Bye, everyone.